When you're learning math, textbooks will often just throw a new definition at you, without any justification for where the definition came from. Like this one, for the Moebius function, one of the central functions in number theory. For people like you and me, this is quite intimidating. It often makes me feel like I'm missing some kind of secret knowledge that would allow me to pull this kind of definition out of a hat. The truth is, of course, that mathematicians didn't pull this out of a hat either. They went through a long and winding process of discovery, dead ends, and carefully investigating many different cases. The textbook only presents the end result of this process. In this video, we will follow the steps one at a time. It will lead us from polynomials and power series to a simple but versatile new operation on sequences of numbers. We will dip our toes into some group theory and finish with number theory. By the end, not only will this weird definition make sense, you will walk away feeling that you could have come up with it yourself. Step 1 is easy. Take two polynomials, say both of degree 3. Multiply them together. You do that by distributing one of the sums over the other. Then you take all the terms for equal powers of x and you group them together. What you may notice is that the coefficients of the product follow a very simple pattern. Here the exponent is 3 and the indices on the a and b coefficients always sum to 3. You will find this pattern in the coefficients of any two polynomials you multiply. It even works for power series, which you can think of as polynomials with infinitely many terms. Just distribute as before and group the terms of equal powers of x. The sum of the indices is always equal to the exponent of x. Let's take a specific example more slowly. How many ways can we make x to the 4th power? Well, we can multiply x to the 0 with x to the 4. Or x to the 1st with x to the 3rd. Or x squared with x squared, and so on. It should be easy to see where the pattern is coming from. If we forget the powers of x, we can just treat the coefficients as two sequences of numbers. We then obtain the sequence for the product by running two frames across the sequences, one coming from left to right and the other from right to left. We multiply the numbers in the frames pairwise and we add everything up along the way. Since one frame starts at 0 and the other at, say, 4, and then they move in opposite directions, the sum of their indices is always 4. This process is called a convolution, and you should think of it as an operation that takes two sequences and produces a third one. Convolution is useful in many contexts, and I left a few links in the description if you want to learn more. Step 2 is fun. We're gonna get creative and try something new. Instead of putting the x in the base and the integers in the exponent, let's flip that around. We put the x in the exponent and successive positive integers in the base. Oh, and we also start at 1 this time, because 0 just causes too many problems. Like we did before, we want to find out what happens when we multiply two of these weird series together. We distribute one sum over the other, and then we group the terms together that have an equal integer value at their base. You should really try this yourself. It's a little different than before, and it reveals an unexpected but very interesting pattern. For the first power, all we have to do is multiply a1 with b1. Easy peasy. For the second power, we multiply this pair and this pair. Those are the two ways of getting 2 to the x. How can we produce 3 to the x? Well, again, there are only two ways. We can combine 1 with 3, or 3 with 1. Okay, try 4 to the x. We can get the 4 in the base by multiplying 1 with 4, 2 with 2, or 4 with 1. There are exactly 3 different ways of getting 4. Do you see the pattern yet? If you try a few more, you will notice that this time it's no longer the sum, but the product of the indices that equals the integer in the base. This explains why there are 3 ways of getting 4. The number 4 has exactly 3 divisors, and each of those provides a unique pair of indices that multiply to 4. Again, if we ignore the exponentials and focus on the coefficients, we have 2 sequences of numbers. To obtain the sequence for the product, we can use our 2 frames again, but this time we have to make sure that the 2 indices multiply to the target number. A different way of putting this is to say that we should frame only the divisors of our target number. The expression for the sum makes this explicit. We sum over all divisors of n. This new operation on sequences is called the Dirichlet convolution. It plays a central role in number theory because it's related to the prime numbers. Whenever your target number n is prime, there are only 2 possible combinations to obtain it. For other numbers, you get more possibilities, depending on their divisors. 6 can be written as 1 times 6, 2 times 3, 3 times 2, and 6 times 1. So there will be 4 different terms in its formula. As an exercise, see if you can explain why most integers have an even number of possible combinations. But for squares, such as 4 and 9 and 16, the count is odd. This is a simple but instructive little fact that you can try to prove. If you need a hint, here it is. By the way, we would get the same result if we move the exponentials down into the denominators. Written like this, the expression is called a Dirichlet series. The multiplication process works exactly the same, so it still uses the Dirichlet convolution. In step 3, we dive deeper into the Dirichlet convolution. I want you to get a good feel for it, and there's no better way to do that than to look at a few examples. Here's a sequence of 1s. Boring, right? Well, remember that these numbers are really the coefficients of a Dirichlet series. The series with all 1s is known as the Riemann zeta function, and it's one of the central objects in number theory. It holds secrets about the distribution of prime numbers. So this humble sequence of 1s is actually a big deal. I will call it 1 bar. Now, watch what happens when we take the Dirichlet convolution of 1 bar with any other sequence f. One of the frames always contains a 1. The other frame visits each of the divisors of n exactly once. So what we end up doing is just adding up all the values of f at the divisors of the target index n. We will now shift our perspective ever so slightly. I want you to think of f as a function instead of a sequence. It maps every natural number to the value at that index. So if you give this function an input of 7, it gives you the 7th number in the original sequence. Okay? Sequences are functions. We can now interpret our convolution with 1 bar as saying the following. For every input n, apply the function f to all of the divisors of n and add up the results. And this works for any function f you can come up with. So, for instance, if f is the identity function, which maps each number to itself, then the convolution with 1 bar simply gives you the sum of the divisors of n. This is known as the divisor function sigma 1. So we have now discovered a very nice little expression for sigma 1. We can write it as the Dirichlet convolution between 2 very simple sequences or functions. And I probably don't have to tell you that the sigma 1 function plays a huge role in number theory. For example, you can use it to define the perfect numbers, whose sigma 1 value is exactly twice the number itself. 6 is an example of a perfect number, and so is 28. Another interesting possibility for f is 1 bar itself, Instead of adding up the divisors, this time we just count how many there are. You can see that every prime number has exactly 2 divisors, 1 and the number itself. Other numbers have an even number of divisors, except for the squares, as I mentioned earlier. This function that counts the number of divisors is called sigma 0. You can experiment with other functions if you like. Try f of n equals n cubed. The convolution gives you the sum of the cubes of all divisors of a number. This function is useful in the study of modular forms, but we can't spend any time on that here. The Dirichlet convolution with one bar is so common and so useful that it has been given a name. It is known as the Moebius transform. It turns one sequence into another. We are already at step 4. This one is a bit more abstract than the others. It all begins with this extremely simple sequence called epsilon. It returns 0 for every input except for 1, where it returns 1 itself. When we perform a Dirichlet convolution between epsilon and any other sequence, the 1 and the zeros conspire to give us an exact copy of that sequence. This seems fairly pointless until you realize that epsilon acts as a neutral element for Dirichlet convolutions. That's a concept from group theory that you're already familiar with. The number 0 is the neutral element for addition, because it doesn't add anything. For the same reason, 1 is the neutral element for multiplication. The empty string is the neutral element for string concatenation, and so on. See our earlier video about monoids for more examples. Once you have a neutral element, you should immediately ask about inverses. Under addition, 5 and minus 5 are inverses of each other because they add up to the neutral element. When you do something and then you undo it, you haven't done anything at all. And that's the neutral element by definition. So the natural thing to ask is, do our integer sequences have inverses? If I give you a sequence f, its inverse will be another sequence g, and by definition, the Dirichlet convolution of f and g must give us the neutral element epsilon. When we write this out for each of the indices individually, we get a set of equations that we can solve to find the values for g based on the given values of f. The first equation is the most important one. It tells you that in order to have an inverse, f1 must be non-zero. g1 is then just 1 over f1. In number theory, most of the sequences or functions begin with the number 1, which is non-zero. So in practice, the first equation will always have a solution. And what's also cool is that g1 itself will turn out to be 1 as well. That's interesting. It means that if we limit ourselves to sequences that begin with 1, the set of those sequences is closed under inverses. It's also closed under convolution. This means that it's a group. And that in turn means that we can now bring all of the amazing tools, tricks and techniques from group theory to the party. Okay, now that the first equation is trivially solved, the others become easier. You can always just substitute earlier values for g into the equation, leaving only a single unknown. So yes, any function that begins with a 1 always has an inverse. We are getting close to our final goal now. Since 1 bar is such an important sequence, we will calculate its inverse. This inverse of 1 bar has a name. It's called the Moebius function, written with a Greek letter mu. And why is this function so important? Well, being the inverse of 1 bar turns out to be a kind of superpower. Remember that convolution with 1 bar is called the Moebius transform, and that it gives us many of the functions that are used all over number theory, such as sigma 0 and sigma 1. The superpower of mu is that it allows us to go in the opposite direction. given an important number theoretic function g, we can now find the associated f. Think of this in terms of decomposition. Mu is a tool that automatically decomposes g into a convolution of one bar with something else. All you have to do is convolve mu with your number theoretic function g. It takes only a few simple calculations to show that, yes indeed, this gives us the f we are looking for. I know this part of the video is probably the most dense and abstract. But hey, at this point at least we finally understand what the Moebius function is for. Instead of the incomprehensible definition at the start of the video that tells us what mu looks like, we now know what it does. It inverts the Moebius transform, getting us from the output back to the input. It's not what you are that defines you, it's what you do. And that brings us to step 5, the grand finale. This is where we calculate the Moebius function. Since we defined it as the inverse of one bar, it has to satisfy these equations. These are just the equations for an inverse we found earlier, but now specifically for the inverse of one bar. Mu of 1 must be 1. And for any other number n, the sum of mu over the divisors of n must be 0. An example will make this totally clear. Let's say that n is 30. To make our calculations more structured and systematic, we will organize all of the divisors of 30 into a Hasse diagram. Creating such a diagram is quite easy. Start with a 1 at the bottom. Put the prime factors of 30 above it. Then write down all the products of two prime factors. At the top, 30 itself is the product of all three prime factors. So one property of this diagram is that each level has one more prime factor than the level below it. But the crucial property for our purposes is that if you pick any number in this diagram, all of its divisors can be found below the number. The divisors of 15 are here. And the divisors of 10 are here. We include 1 and the number itself, so that we get a part of the diagram that looks like a diamond. The equations for the Moebius function tell us that the sum of mu over all the numbers in any diamond shape must be 0. We already established that mu of 1 should be 1. For the prime factor 2, the mu values in its diamond must add up to 0. Since we already have a value of 1 below it, the mu value for 2 itself should be minus 1 to compensate. That's how we end up with a total of 0. The same goes for the other prime factors, 3 and 5. Mu should map them all to -1. At the next level up, we already have 4 divisors to take into account. One of them adds 1 to the total, but the other two each decrease the total by 1 again. So, in order to get the total sum to 0, we have to give the new number a mu value of +1. This happens for all numbers in this layer of the diagram. 30 itself has 3 prime factors, and some simple counting will tell you that it needs to decrease the total by 1. So, as we go up the diagram, and the number of prime factors increases, the required value for mu keeps alternating between 1 and -1. In other words, if a number has an odd number of prime factors, mu has to map it to -1, and for an even number of prime factors we must have 1. There is just one more case we have to consider. For a number like 24, we get repeated prime factors. After reaching this point in the diagram, the total mu value over all the divisors is already 0, and we want to keep it at 0. So whenever a prime factor repeats, we are forced to map that number and all numbers above it to 0. Putting this all together, we get this conclusion for what the Moebius function should look like. And what do you know? This is exactly the same definition we found in our textbook at the start, give or take some additional terminology like square-free. If you ever struggle through a textbook wondering how on earth mathematicians can come up with these crazy definitions, remember that the textbook only shows the polished results. In reality, the definition and the underlying theory were slowly uncovered over many decades or even centuries by thinking about polynomial multiplication and inverses and group theory and prime numbers. Over time, the definition kind of presents itself. It's inevitable and not nearly as arbitrary as it seems. I hope this video inspires you to be interested in number theory. We are planning to publish more videos about that topic in the future. This one was our entry for this year's Summer of Math Exposition contest. So I want to end with a big shout out to Grant Sanderson and his team for organizing the contest so flawlessly every year. It's going to be another interesting summer full of cool discoveries.